Good day, everyone. Today, I'll be talking about one of the most important concepts in geodetic surveying, the reference coordinate system. A reference coordinate system defines a uniform framework for positioning points on Earth's surface. By using a common system, surveyors and engineers ensure that all measurements are referenced in the same way. Without a consistent reference coordinate system, data collected from different times or places may not align, leading to errors in mapping, boundary identification, and engineering work. Because the Earth is not a perfect sphere and shifts slightly, a reliable coordinate system anchors our measurement to a known model of the Earth. This brings accuracy, compatibility, and repeatability to surveying and geodesy. Now, let us define what a coordinate system is. A coordinate system is a mathematical construct that lets us assign numbers to locations on or near the Earth's surface. In geodesy, we frequently use three main types: geographic coordinate system, or GCS, which uses angular values or latitude and longitude on the Earth's surface; projected coordinate system, or PCS, which takes the curved surface and flattens it into a plane, typically using linear units like meters or feet; Cartesian coordinate system, or CCS, which represents positions in three-dimensional space, often with origin at the Earth's center of mass. Each type has its role: GCS for global reference, PCS for local maps, and CCS for 3D spatial modeling and satellite positioning. Now, let us talk about what a reference frame is. A reference frame defines the Earth's size, shape, orientation, and origin in space. It is the underlying model that gives all coordinate systems their meaning. Using a consistent reference frame ensures that all positional data are properly aligned. For example, WGS-84 is a global reference frame used for satellites for worldwide positioning. In the Philippines, PRS-92 is a national reference frame aligned with WGS-84 but adjusted for the local geodetic network, ensuring high accuracy for national surveying and mapping. Without the correct reference frame, coordinates may appear correct locally yet not matched internationally, which can cause errors in multi-region surveying or when integrating global data sets.
Are you wondering what's the real shape of the Earth? Is the Earth really round? Does its shape have impact to surveying jobs or geodetic computation? To answer, we need to understand the difference between the geoid and the ellipsoid. The geoid and the ellipsoid are two fundamental models used to represent the Earth's shape. The geoid reflects variation in gravitational forces, while the ellipsoid offers a simplified, mathematical precise shape that is essential for geodetic computations. While we often think of the Earth as a sphere, our planet is actually very bumpy and irregular. The geoid's irregular shape is a consequence of gravitational variations across the Earth, which are influenced by factors such as topography and density of materials. The geoid is a model of Earth's precise surface elevations. Areas in yellow and orange have a slightly stronger gravity field as a result of the Rocky Mountains. The ellipsoid is defined by its semi-major and semi-minor axis. Earth in this representation is like a pizza dough. If you spin it around, it will flatten and spread out. The ellipsoid is a mathematical model that approximates the geoid with a smooth, regular shape, simplifying calculations. It is defined by mathematical equations, enabling easier computations of distances and areas. Practicality of using the ellipsoid. First, the ellipsoid provides a smooth, mathematically defined surface. It closely approximates the Earth's shape, improving accuracy, enables simpler and faster computations of coordinates, distances, and areas, more practical than the irregular geoid, which varies due to gravity. Use direct mathematical formulas for positioning. Previously, we have tackled the geoid and the ellipsoid. Now we will discuss the relationship between the geoid, ellipsoid, and the topographic surface, including how they relate to height measurement. As we all know, the geoid is used as a true reference surface for measuring elevations because it closely follows the mean sea level. It is also an equipotential surface of Earth's gravity field, meaning gravity acts perpendicular to everywhere. And the ellipsoid is used as a mathematical model that approximates the geoid with a smooth, regular shape, simplifying calculations. And topographic surface. This is the actual physical surface of the Earth, the one we live and measure on, including mountains, valleys, and plains. When talking about height, we need a scale to measure. The essential part is we need to have a smooth surface from where to measure, but standing in a stool or an object doesn't mean you have a greater heights. The sole of our shoes and the floor are the surface to measure the heights. The geoid's deviation from an ellipsoid ranges from 85 meters in above to negative 106 meters below the ellipsoid. The geoid matches more or less with mean sea level and is constantly changing because of the sea's motion, and it's affected by tides, wind, and atmospheric pressure, temperature, and so forth. So orbiting satellites provides constant update of the latest data. Here's a representation. This is a topographic surface, while mean sea level and geoid matches closely with, and the ellipsoid in the green line. And imagine you are standing on top of a mountain, and you might wonder what is your height, and from where do you actually measure your height from the top? The green arrow represents the ellipsoidal height of view, which is above the ellipsoid, but it can be below ellipsoid also. And this yellow represents the orthometric height, or the height above the mean sea level. Since the geoid and ellipsoid give us our vertical reference frame, now we're going to know the horizontal reference frame concept. But first, we need to understand coordinate transformation. A coordinate transformation gives the surveyor the ability to move position or location information from one coordinate reference frame to another. The initial measurements that were used to generate the coordinates are not necessary. Think of it like translating a word from one language to another. The underlying meaning, the real location, stays the same, but the way it is expressed, the coordinate values, changes. According to Jiri Mahmoon, there are three elements of transformation. 1. Scaling is used to increase or decrease distances between the points in order to make them fit in the new system. 2. Rotation rotates the coordinate system around the point or axis by a specified angle. Number 3. Translation moves the origin of the coordinate system without changing its orientation. Why is it necessary? Here's why. Different datums have different reference points. Different maps and projections distort the Earth differently. To further explain the concept of coordinate transformation, here's a scenario that Jerry Mahon used, where two surveyors surveyed a property. Surveyors assumed their own coordinates and line direction, but surveyors have good closure and complete coordinates for their lot corners. Today, you are hired to do a survey for the two lots. You decide to plot both their surveys in CAD. The result? The coordinate systems of the two surveys are different. They have different coordinate origins and meridian directions because each surveyor assumed his own starting coordinate and direction independently of the others. To resolve this problem, we need to move Lot 3 into Lot 4 system or Lot 4 into Lot 3 system. We can now perform coordinate transformation. Since we all know coordinate transformation, figure J5 illustrates a situation similar to combining both surveyor surveys. The same 2 points A and B have two different positions. The two from systems are two coordinate references. The two system is a target where all positions will be expressed. Points AF and BF, the from system, are identical to AT and BT in the two system.
So next is, how do surveyors determine exact locations on Earth's surface with high accuracy? In geodetic surveying, this is made possible through the Global Navigation Satellite System, or GNSS. It uses three main methods, which is point positioning, relative positioning, and kinematic positioning to locate points precisely on the Earth. Point positioning uses a single receiver to get coordinates from satellites common in basic GPS navigation but only accurate within a few meters. This positioning uses two receivers, one known and one unknown, to cancel out errors, giving centimeter level accuracy ideal for land surveyors and construction. The last one is kinematic positioning, or real-time kinematic, works while moving, such as on drones or vehicles, for accurate real-time mapping. So next is, how do surveys accurately describe locations on Earth? They use coordinate system, mainly the geographic and Cartesian systems. The geographic coordinate system uses latitude, longitude, and elevation to locate points on Earth's curved surface. While this coordinate system is easy to visualize in maps and commonly used in GPS and navigation, but it's less precise for 3D measurements since the Earth isn't a perfect sphere. Meanwhile, the Cartesian coordinate system represents positions using x, y, and z values from the Earth's center in a 3D rectangular grid. This coordinate system is ideal for accurate computations and satellite positioning, but harder to visualize as it requires conversion back to latitude and longitude. And the last part is, how do coordinate systems and positioning methods relate to a real-world surveying and mapping? In surveying and mapping, coordinate systems and positioning methods play a vital role in determining accurate locations on Earth. Geographic and Cartesian systems describe positions through latitude and longitude, or x, y, and z coordinates in 3D space. These are applied in land boundary surveys, mapping, and engineering design. Positioning methods like point, relative, and kinematic positioning offer different levels of accuracy. For instance, relative positioning is used in construction and boundary surveys, while kinematic positioning is applied in drone mapping and navigation. Together, these systems and methods make modern surveying more precise and reliable.